waves and scattering. And there's two kinds of scattering that the book talks about that we're going to be concerned about in this course. The first is elastic scattering, and elastic scattering means, what that means is that no energy is lost. But in the context of wavelet theory, where you have a wave that's made up of a bunch of wavelets, so of course if you have a plane wave, you can imagine that there's lots of little wavelets that make up every point on this plane wave. This is the Huygens principle that you probably learned in college, and these little wavelets add to make wave. Okay, so elastic scattering, another way to think about that, is that the waves are going to conserve the phase. We'll get to that in a minute. Let's first just talk about what this elastic scattering is. Of course, it's what's important in diffraction. So diffraction is elastic. I should put cooperative. Scattering, oops, from a group of atoms. Okay, so let's think about what a wave looks like. So an electron wave front. So remember, electrons can behave like waves, they can behave like particles. We're going to talk about the fact that they're going to behave like waves. So if we have a wave function, psi of position and time, and of course I'm just drawing this in one dimension to make it easy, this is going to equal psi of kx minus omega t, where k is the wave vector and omega is the angular frequency. So let's just write that down. K is defined as the wave vector, and omega is defined as the angular frequency. Okay, this is in 1D. It's important to remember that this kx is minus omega t is dimensionless. So, and this is called kx minus omega t is the phase of the wave. All right, let's stay in 1D. In one dimension, and we're going to look at a sinusoidal wave. So in a sinusoidal wave, limited to region L, so if we do this to a region L, we're going to have psi of x and t is equal to 1 over the square root of L over the length, e to the I kx minus omega t. Wow, that sure looks different than what we were talking about. You might remember that in this region L, this is a sinusoidal wave function. How to remember that? Well, remember De Moivre's theorem that says e to the I kx equals cosine of x plus I sine of kx, of x. And so that's how you get the complex variable in this. And that's pretty important. So again, let's write down what we've got. we have psi of x and t equals 1 over square root of L times e to the I kx minus omega t. So here, psi of kx minus omega t moves to the which side? Well, when we're taking something away from this is getting bigger, so it moves to the right or more positive with phase velocity omega over k. Okay, so phase velocity equals omega over k. If you have psi of kx plus omega t, implies that it moves left, again with the same phase velocity. So the question is, what's this about? Why 1 over square root of L? Well, the answer is normalization. You want to have the probability density, the intensity, and of course this is again in one dimension, is going to be a probability density. And we know from quantum mechanics and what a wave function is that the probability density is psi star psi. Okay, all in 1D. So if we take our wave, the only way, if you integrate this over all space, then the probability of finding something has to be 1. So you have to find it somewhere. So that implies that I1D equals 1 equals psi star psi. And so if we look at the complex conjugate, which is psi star, we get that that's 1 over square root of L times e to the I kx minus omega t. Well, that's psi, so psi star times 1 over square root of L e to the I kx minus plus omega t. Well, we'll just do it this way, minus kx. So minus kx minus omega t. That's the complex conjugate. And if you multiply these things together, this equals, this is going to simply equal, where am I? This is going to equal 1 over L, because this, if I change my color here, that didn't change my color. Still didn't change my color. Oh well. This term times this term is 1. 1 over square root of L times 1 over square root of L is 1 over L squared. So what does that mean? This means that the electron will be somewhere between 0 and L. One chance within L. That's what it means. So to find the probability, p, we're going to integrate from 0 to L the probability distribution in 1d dx, which will equal the integral from 0 to L of dx over L. And if you do that, you see that that equals 1. So that's our proof.